little bit, well, at the start trying to motivate why you might want to do physics, but many of you or all of you have already shown some interest. So this is kind of like preaching to converted, but fine still. Why would anybody want to study physics at all? The number one reason really is, do you like physics? Or essentially at the moment even, do you like solving problems or puzzles? Because if you do, you're basically already doing what I would consider to be doing physics. So the number one reason is because you like it. Of course, it's really important in many different ways, right? To understand the world around us, even the world inside us, the world beyond us. Many, many important inventions and technologies are developed by physicists. And the great thing about physicists is that, well, we're extremely versatile problem solvers, which means that you have great career opportunities if in a vast range of fields, if you have any degree in physics at all. So for example, it could be something just like answering the simple questions that, you know, even a child can ask, like, you know, a young toddler, like, why is the sky blue? Why is your plate cool in the microwave? Why are metals shiny? And so on. So you can learn all these things, but obviously you learn a lot more advanced things as well. But one extremely important setting point for physics is that you get jobs. Everybody who I've ever come across coming out of UCC or anywhere with a physics degree who wanted a job, got a job. And it's what people might consider an excellent preparation degree, because of the fact that we're making problem solvers. You learn to consider any problem. You learn how to think about solving a problem, regardless of the type of problem it is. So the context, it doesn't really matter. You learn how to solve problems. And this is desirable in all fields. So the examples of the careers I've written here, I know people who did physics degrees in UCC, who got jobs in all of these different areas. And this is only a small sampling of it. So people who could end up in journalism, law, many people in finance, medical physics, science and engineering itself, of course, people going on to do work in computer science, like working for Apple or working for Google, astronomy, biology, many, many, many more. So people get jobs out of the physics degrees in, I mean, you name a job, then no doubt you can find a physicist doing it. Now we have two entry streams to physics degrees in UCC. The first one is the traditional CK408, which is physics and astrophysics. And the second one, which is a bit newer, is CK409 industrial physics. So I'll talk a little about them individually. So let's just talk about the physics and astrophysics one first. So this is kind of traditional physics degree version. There are a lot of different degrees actually you can come out at the end if you enter through CK408. So there's the two that you would expect the course straight away. You can do BSc in physics, and you can have a BSc in astrophysics. They're actually very similar, but the astrophysics is a bit more centered on astronomy and astrophysics and things. I'll talk about it again. And we also have what I'm calling here physics plus something else degrees. So where you do physics and maths, or you do physics and chemistry, or maybe physics and education. Okay, so this is basically true for anybody coming into any of the physics programs in UCC, but particularly for the BSc in physics. So you get fundamental training across the whole range of physics. So classical physics, what we might consider slightly, you know, pre-20th century physics, quantum physics, electricity, magnetism, the very cool things like relativity, photonics, things to do with material physics. You may not have heard of the Tyndall National Institute, but it's a very internationally, globally renowned research institute. It's part of UCC, but it's off campus, but it's very strongly affiliated with the physics department. Many of us have appointments both in Tyndall and UCC. So it's a great resource for the department to have, for having guest lecturers, for doing projects in particular, absolute world-class facilities. It's a really cool place. But of course, what we're really teaching you through everything are problem-solving skills. The department has a few research specialities, quantum technology, which is a really hot topic at the moment. So things like quantum computers and so on. Photonics, which is using light in order for technology. So, you know, you might consider the internet is almost entirely powered by photonics at this stage, using lasers and optical fibers and so on. Then the structure of matter, electronic structure theory, more work with lasers, and of course astrophysics as well. So you get to see researchers are teaching you these things all the time, offering projects in these areas all the time. So you get a lot more than just the regular interaction with staff just in a lecture theatre. There's a lot of research informed teaching as well. Then if you do the BSc in astrophysics instead, well, it's really like the physics one. You know, it's the same fundamental background. You're getting the same math skills essentially. You're getting the same kind of numerical skills. Of course, there'll be some coding skills as well as the people who are doing the physics degree. And in fact, for first year and second year, there is no difference. You're in exactly the same classes all the time. In third and fourth year, then that's when it's slightly different. If you're doing the astrophysics, if you're doing the BSc in astrophysics, then you have to, of course, do the things like astronomy. You have to do things like cosmology, and you have to do things like general relativity. And that's what makes it a BSc in astrophysics rather than in physics. But of course, actually, the people doing the BSc in physics, they can also take all these astronomy courses if they want. It's just that their degree will be called the BSc in physics instead. And the department has a really strong astrophysics concentration. It's still growing, in fact, working both on theoretical astrophysics and experimental astrophysics, and with cool collaborations, saying here like people in Chile or Hawaii, or even, you know, with space telescopes and so on. And people doing the astrophysics degree do projects specifically in astrophysics, where you'll be dealing with real data that could be coming from NASA or from the European Space Agency or from one of these telescopes around the world. And of course, again, the problem solving skills, you're getting those all the time. One of the things which hopefully should be starting again is that people in third year doing the BSc in astrophysics typically would get to go to a research class telescope at an international observatory. So this would happen in third year. Hasn't happened for the last few years, of course, for the obvious reasons, COVID, but it should be something that's coming back in again. But of course, even if everybody doesn't get to do that, you do final year projects that will involve data from these international observatories anyway. So you interact with researchers from different places all the time. So there are two single honors degrees, let's say, where you're doing physics, you're doing astrophysics. Then we have the ones that are the physics plus something else. So you could be doing a BSc joint honors physics and mathematical sciences. So what that is basically, half your modules are in physics and half of them are in maths. They could be in maths, they could be in applied maths, they could even be partially in financial maths. So this is obviously then you'd be a member of the department or school of physics and the school of maths. So for people, of course, then who maybe find that they're really strongly interested both in maths and physics, this is a nice way of doing it. You can do this just by coming into CK408. You will, at the start of the year, have to make some decisions about the courses and the modules you choose to make sure you can do this, but everybody gets a mentor and we can help you out making sure you're choosing the right things so that you don't close off any avenues. So a lot of people choose to do that, which is half physics, half maths. Then we have one which is the BSc in chemical physics. And of course, then that's more or less half physics and half chemistry. And that's in conjunction with the School of Chemistry. So these options, of course, are also open to people who come in to CK407, for example, in maths. They could come into maths and choose to do half physics and half maths as well. And then we have a BSc in science education as well, which is with the Department of Education in UCC, where you do a lot of education modules and physics modules in order to become a physics teacher. Okay, so they are our CK408 programs. We also had, in the last few years, introduced a new program, which is CK409, the BSc in Industrial Physics. Now, this is a joint degree program between UCC and MTU, the Munster Technological University, so that used to be CIT. And this is really exciting if you're really into hands-on things and you are sure that you want to walk into, you know, a job immediately at the end of the program. So it combines fundamental physics. So in some sense, you're kind of getting the fundamental physics training from us in UCC for half your time, and then this very modern advanced industrial training in MTU. But of course, in practice, actually, we're also giving you some industrial training, and they're also giving you some fundamental teaching as well. But that's roughly kind of the way it is. And then this opens up the path to careers in loads of exciting and innovative industries. So just for example, even in Cork, you know, we have Janssen, Pfizer, Novartis, Alcon, Boston Scientific, we many, many, many others who are all interacting with this program already, BSc Industrial Physics. So just to spend a little bit more time talking about industrial physics, what even is an industrial physicist? Well, I'm saying here the same thing you've heard me say loads of times now already. Industrial physicists are problem solvers. But the difference here is they need to quickly solve problems in a wide range of industrial settings. So when you're working in an industry, of course, you have a problem to solve. They want you to solve it like that. You need to be able to solve it, and you need to be able to solve it with whatever resources and equipment that are there. So you might have to come up with something new, some unconventional technique as required. And then, of course, industrial physicists are employed in all these and more really important areas where they're extremely important for global health, for water, for energy, of course, the environment, and so on, food, education, security, poverty, everything. Industrial physicists will have roles to play in these areas. So again, this is kind of recapping a little what I was saying earlier. There's very obvious conventional examples of where people can get employment as an industrial physicist. You know, the very obvious ones: biotech, pharmaceuticals, medical devices, maybe working in optical imaging, telecommunications, so working with lasers and so on. Of course, there's also the unconventional examples. People can work in something that you mightn't typically associate with physics at all, but it absolutely does happen. So this is just a little example of the types of technologies and so on that have been developed by industrial physicists. Okay, so things like electronics, of course, you know, radio, television, computers, silicon chips, and so on, semiconductors. These things are all originally, more or less, discovered or are improved on by industrial physicists and physicists. High-speed telecommunication networks and GPS, right? Of course, GPS absolutely couldn't work at all without theories like Einstein's theories of relativity. You absolutely need it, or else the clocks that you have and the position finders and so on that you'd have in the satellites would be wrong within just a few seconds. So extremely important for things like that. Medical technology, so X-rays, MRI, lots of new imaging. It's actually a huge thing in Cork and in UCC in particular, working on medical technology now and what might be called biophotonics. So using lasers and using light in maybe in hospital settings. Okay, so plenty of other things. I don't have to read them all out to you. But basically all the things that are making up the modern world, I didn't even write the internet here, but of course it's kind of inside the networks, the communication networks, but the internet is entirely dependent for its speed and so on optical fibers and lasers, which of course were things invented and developed by physicists. Okay, so that's kind of repeating. What was the rationale behind the program? So really it was to address this global skills shortage. There's a huge demand from industry to have advanced instrumentation and automation and so on. And it's preparing for its so-called Industry 4.0 revolution. Now, one of the major selling points and things that are in the industrial physics program that are not in typical physics programs or maths programs or even many engineering programs at all is a work placement. So in the third year of the industrial physics program, you do a minimum of a 10-week work placement. So you go to several of the companies that I was mentioning. There's many, many more, but you go and work for them for 10 weeks. And then typically what actually happens is the company wants you to work actually much longer for them. So people often end up working with the company for the summer. It doesn't have to happen, but it typically does. And you get a paid job then for the summer. And then what we're finding is that even before the people go back in the fourth year, the companies are really saying, we want you back next year. You practically have a job sorted out already. The people in industrial physics, I mean, they're, you know, it's almost a struggle to make sure that they actually finish their fourth year instead of just heading out into a company straight away. The companies are crying out for them for the placements, and they're crying out for them as graduates. So it's just some of the logos of the companies, but all or many of these companies are involved in these placements, in particular with MTU, the MTU side of the program. And like I was saying, there's a huge demand for graduates. And the slight difference is, I know I was saying already that I don't know anybody who wanted a job when they came out of physics who couldn't get one. And that is absolutely true. And we have companies coming every year, like Apple come to us and Accenture and other companies saying, can we give presentations to your fourth years and try to persuade them to apply for the graduate programs and so on. But the key there is you really are going into a graduate program. Now, it ends up being an amazing job, of course, and they're really sought after jobs. But the industrial physics students are immediately walking into these companies and going to work without needing a graduate program. Now, they could go and do some of those other jobs as well where they do the graduate programs. But, you know, companies like Boston Scientific and others are crying out for them just to come in immediately. So they're going in with these great jobs right out of fourth year. Okay, so I've been harping on this already to you, but after UCC, after you finish with your program, well, there are many career paths. Everybody loves problem solving skills. And so you're in absolute huge demand straight away. Again, these are some of the companies, but here is just a little list I put together of companies in Ireland that employ physicists. It's absolutely non-exhaustive. There are way more than this. It was easy to just find even this many, but you can see the same idea that I was saying earlier. Some are completely obvious. The companies that have laboratories in their name, analog devices, just looking through, Ablana Photonics, you know, General Electric and Google, of course, Rockley Photonics here, Motorola, and so on. Then NASA, you know, plenty that are completely obvious, then some that aren't obvious at all necessarily. So like Citigroup, Deloitte, Accenture, you know, professional services, investment banking, banks, Bank of Ireland and so on, Allied Irish banks, hospitals, of course, which is a really growing area. Medical physics and is becoming extremely important everywhere. And like I said, anyway, PricewaterhouseCoopers, Pfizer, it's a huge list. Everybody wants to employ physicists. This is a graph, which in fairness now is a bit old. Unfortunately, I couldn't find a more recent one, but this was one that was put together. So it's about 10 years old now, but it's still somewhat true, I'd say. So if you're looking at people who did physics degrees, okay, and how many of them continue then in whatever role? Well, how many of them actually continued in physics and astronomy? Surprisingly low, only about 3%. Then people who stayed specifically in science, technology, or engineering, apart from engineering here, let's say 13%. 30% go into what you might call an engineering position. 24%, I'd say that could even be higher now, people going into computer and information systems, because of course you get a lot of a lot of training and coding and so on in any physics program anywhere. And so companies like Google and so on absolutely love hiring physicists. I remember 2 years ago as well, somebody who did a project with me who went immediately into a software company. And then this might be the surprising thing, almost a third of people end up not doing STEM things at all. So I know I've said it loads of times already, but really you could go into any area and you'll be in huge demand. Okay, so this is just going back to the things I said at the start. This is the number one reason why you might choose to study physics, because you like it. It's very important for basically understanding everything. But there's great career opportunities. You'll learn to be an extremely versatile problem solver if you do a program in physics. Okay, so anyway, that is basically the end of the presentation that I was going to give, but some of you already sent in some questions. So I'm just going to answer some of these questions now in the next few slides here. I've sort of split them up into different categories, and some of them are very similar in themes already. So these few were entrance type questions. So questions I think that sort of meant in going from school into, let's say, into UCC doing physics. So one was, how important is taking physics for the Leaving Cert? I would say not important at all. We assume when you come in that you haven't done physics. We don't take anything for granted. It's, and this, what I was about to say next relates to the next question as well. Maths is much more important. So, you know, if you already really dislike maths, then doing physics in UCC would be a bad idea. But physics itself in secondary school is not really like physics necessarily in university at all. If any of you are doing applied maths, that's actually something that's much more like what I would consider physics to be like in university. So then how good does your mathematical ability need? And by the way, we don't, you obviously, because I'm saying it's not important to do physics at all beforehand, it's not a requirement. You don't have to do physics in order to come into any of the physics programs. So then how good does the mathematical ability need to be to do physics at third level? Similar question, can you study physics without a H4 in maths? Well, it's pretty important to be good at maths and to like maths, I would say. That's more of an indicator about how you'll get on than whether or not you're doing physics. You can technically study physics without a maths H4. So these are the requirements here. You need a H4 in either a lab science subject, in maths, or in applied maths, or in computer science. Okay, so you can get a H4 in any of these things, and the lab science would be biology, chemistry, physics, physics or chemistry, and agricultural science. But if your H4 up here is in maths, or applied maths, or computer science, then you also need to have done a lab science and get an 06 or a H7. But it means that you could actually do it without having a H4 maths. But I must say, if you think that a H4, you'd want to be getting a H4 right in order to be comfortable in physics. And is French necessary? It's not. These are the requirements in order to get into the physics programs. So there's no extra language requirement. Okay, so that's the entrance type questions. Then what I'm calling the kind of during UCC type questions. So let's say you're already in there. Are the courses transferable? So if you came into physics, could you transfer to engineering and vice versa? Like formally you kind of can, but it's pretty unusual and not guaranteed that you will be allowed. And also a little bit awkward because, you have certain modules that you must study, say in first year, in order to be able to do something in second year. And if you haven't done these, then it's very difficult to transfer. It can kind of be done if you decide that extremely early on, like in the first 2 weeks, somebody is in engineering and they decide, oh, really, I would have preferred to do physics, then it kind of can be done. But if it goes past the first few weeks, it gets kind of awkward. Within physics itself, it's actually not that difficult to transfer, let's say, in first year between maths and physics or vice versa. Or it's a little bit more difficult to do between physics and industrial physics, but we can find ways of doing it because, of course, they're both something that are under the control of our department. But I would say it's a little bit unusual to do it, but it does happen. But it's not guaranteed that you could. Are there Erasmus opportunities? So more broadly, I'd say, are there study abroad opportunities? There are. And at the end of second year, at the end of third year, there can be opportunities. Again, you have to apply in order to be able to do it. But people do go abroad for their third year. People quite regularly go to some universities in the States. So for example, people have gone to Berkeley, or they've gone with, one of the real famous universities in the US, or they've gone to universities in Boston, or people go to places in Germany and several other universities that we have links with, that people are able to go and study there for a year. And that counts then, for example, as your third year. You would come back then into fourth year. There definitely are projects. It depends, again, of course, on the program that you're taking, but you're guaranteed to have at least one major project in fourth year, no matter which the programs you're doing, whether it's CK408 or CK409, or whether you're doing physics, astrophysics, joint honors, chemical physics, and so on. You definitely end up doing a major research project. If you're doing physics or astrophysics, there'll only be one that you have to do. If you're doing chemical physics, you'd have two. If it's industrial physics, you'd have one, but you'd also have your placement and so on. And then, of course, there are many opportunities for doing research projects outside of the academic, the undergraduate academic year. So we'd have research projects for the summer where people can come in and work with us on some topic for 8 to 10 weeks over the summer. But they're optional, and voluntary as such, and you apply to do them. And the same with Tyndall National Institute. We have lots of students who end up doing some projects in Tyndall over the summer and so on. Sorry, I probably should say UCC physics course here. Can you switch from theoretical to experimental, or will you just be trained as theorists? No, the UCC physics course is not a theoretical physics course. I mean, you can sort of choose to do a lot of theoretical physics in it, particularly if you choose to do the joint honors, And maybe in the future, we might have a theoretical physics program. It's possible. But right now, the program is physics and everybody does experiments. You definitely do experiments in first year, second year, and third year. And even the people doing joint honors will definitely be doing experiments in first, second, and third year. And, you know, 1 or 2 modules a year that consist of doing experiments. In fourth year, then it becomes an elective, which means it's optional. You can choose to do it, but you don't have to. But it definitely isn't already a theoretical physics degree. It's a physics degree that covers a lot of theoretical physics and actually quite a lot of experimental physics as well. How much of each is a little bit up to you, but you definitely have to do some experiments. And I'm a theoretical physicist myself, but it's very important to get some training, in my opinion, for everybody to see what it's like to have to do experiments in physics. And then these are what I'm calling the post-UCC type questions. So some of these have been answered already during it, and I'll be repeating myself a little here, but how many graduates go into relevant fields? I'm not sure exactly, but you know, you saw the pie chart earlier that said, but you know, the options are there to go into whatever field you want. Basically, if you want to stay doing something technical and sciencey, you can, and you will almost certainly be able to get a job in it. If you'd like to leave science and technology behind at the end of it, you also can do that. So, and people do absolutely take all these different career paths. So here, what direction will your career path go after school? I mean, that, you know, there's the famous thing, how long is a piece of string? That's really depends on the person. And I have classmates who were undergraduates with me, some of whom carried on and did things like went into doing PhDs, became academics like me, or people who did PhDs and ended up working in the semiconductor industry, whom then might have changed and now work, you know, for a biopharma type company, or maybe they work in making, for example, a classmate of mine now was running a lab for Johnson & Johnson and Janssen, who were making artificial knee implants. But then another person who decided they weren't going to follow down a science or a maths type route, and they immediately went working for PricewaterhouseCoopers in management consultancy. So that's just the three of us from, you know, the same class there. Another person who was in the same year as me, who went on to actually be a lawyer, but still found the physics degree really valuable. So your career path is whatever you want it to be later on, and it'll be they're extremely diverse opportunities. R&D opportunities, well, there are plenty of research and development opportunities, well, research opportunities, of course, even as an undergraduate, but then as a postgraduate, well, you can of course do postgraduate degrees in UCC, you can do them elsewhere. You can do master's or PhD programs. You don't have to do that, of course. You can go working for a company. So like people, I think last year, a few people ended up working for Intel. And so working with semiconductor chip, you know, in fabricating semiconductor chips, and they will definitely be doing research and development. And you could say it for anything. You know, lots of people, of course, do go on to do R&D. Lots of people don't, similar to what direction will your career path go. There are huge opportunities if that's the kind of thing you want to do. And what careers are available? Well, every career, essentially. And the same here. What jobs can you specifically get? You can get any job you want practically, but I mean, we genuinely have companies who are coming in to give presentations, asking people to try to join their program. So several people in the last couple of years went working for Apple. I know people were being interviewed recently to go into the Apple finance training program. So not necessarily even technical things in Apple. People have gone into software, people have gone to Intel, people have carried on to do research, people have gone to software companies, practically endless list. Similarly here, you've great study opportunities and they're growing all the time. You know, as more and more things become important. So for example, things that weren't there a few years ago, but are becoming really important now are alternative energy. And that's going to be a huge source of employment for physicists, I would imagine, in the next few years. Are any of the graduates employed in NASA? Well, I don't think so now, but there was somebody who was a year ahead of me who was working in the Jet Propulsion Laboratory in Pasadena, which does a lot of work with NASA, but nonetheless we just recently had our final year projects finish up. So these are the students who are about to graduate now with their BScs in physics and astrophysics and joint honors and so on. And at least one of them was working on a project that involved getting data from NASA telescopes and analyzing some astronomical phenomena with that. So I'm sure that people, if they really wanted, could get jobs at NASA. And for all I know, actually, maybe somebody is. I just don't know of any. But the interactions with NASA do happen all the time, though. And then someone asked, would you recommend to do a master's or PhD degree in UC or do it in another college? Again, that's a really personal decision. Several people every year move on to other places. So last year we had a student go to Cambridge, a student going to Oxford, a student went over to Berkeley in the US. Some students went, I think, to Galway to do medical physics masters. So somebody went to do the master's program in energy engineering in UCC. People stayed to do PhDs or masters in UCC. Some went to MTU, some went to Tyndall. So it's very much dependent on the person, what they're interested in. Do they want to travel? Personally, I think it's wonderful if somebody does go away to another college and do it there. But again, this is something you would decide for yourself. But, you know, at the moment, that's a good 4 years away for all of you. And you learn a lot in those 4 years about whether you would like to go away or not. Okay, that one is snuck in there again for some reason. This was another question I received. So a science type question. What are the roles in biological and chemical findings in astrophysics, such as new elements and organisms being researched? Well, I'm not an astrophysicist. I'm definitely not a bioastrophysicist. So in short, I don't really know, but I'd imagine that this is something that's becoming really interesting, especially now that we're increasingly able to land spacecraft on comets and on other planets and on other moons and so on. So I'd say this is something that's only going to grow. And it's obviously completely fascinating. And then I was sent this one, which I've called the Nobel Prize winning type question. What exactly is time and why does it only move in one way? Well, I would say physicists have been wondering the same thing for as long as people have been studying physics. If you could truly answer that question, you would definitely be getting a trip to Stockholm and getting one of these medals. But, you know, that's the kind of jokey type answer. It's definitely not jokey in that what exactly is time? I would say it's absolutely true. Nobody really knows. There are many different ideas of what time is. Is time truly fundamental, which is what we all kind of feel like time is really a thing that is passing all the time. But maybe time isn't fundamental, maybe it only emerges. And that's a little bit related to why would time only move in one way? And this is something you would learn about, you'd start to learn about in second year if you were doing a physics program in thermodynamics and this concept of entropy, which you probably haven't heard of now, but there's a very easy way of understanding it. You can tidy up a room and the room for sure is going to get messier. And what that means is that entropy basically always increases. Entropy is basically how messy is something. And it turns out that entropy and time are really kind of linked in a very strong way. And entropy basically always goes up, as in things always get messier. And a lot of people think that that's also why time only moves in one direction as well, because things tend to get messier rather than tidier. But you learn and hear about lots of other of these things, hopefully in the next few years when I see you all coming into thermodynamics classes. Okay, so that's it. This is my email address here. My name is Brian Kelleher, and feel free to email me if you have any questions after this. I mean, there's going to be a chance now to ask some questions here if you want, but if you think of something later or you'd rather drop an email, just send it to this. You can find my details again if you don't want to take it down now on the UCC Physics website. This is the department number if you'd like to call. This is the general physics email address, but if you have some specific question you'd like to ask, you're more than welcome to send it to me. Okay, and with that, I'll stop sharing and we're happy to take some more questions if people